That price just locked in. You didn't see the calculation behind it. Nobody does. But here's what's wild. In the 1.8 seconds between you tapping that destination and your phone showing you a driver's name, Uber ran a sequence of operations that most engineers would describe as genuinely hard to get right. 5 million driver location updates per minute across 10,000 cities. I want you to sit with that number for a second. 5 million per minute. And every time someone requests a ride, Uber has to find the closest available driver, not the closest one in the database, the closest one on the actual road, and get a confirmed match back to your phone in under 2 seconds. Today, we're going to follow that request from the moment you tap, all the way to a driver accepting, and understand exactly how Uber built a system that does this hundreds of millions of times a day. On the surface, finding the nearest driver seems easy. You know where the drivers are. You know where the rider is. Just find the shortest distance. And honestly, that's almost exactly what Uber did when they launched. A rider requests a ride. The system queries the database. Give me all drivers within X kilometers. Calculate distances. Return the closest one. That works fine when you have 200 drivers in one city. It works fine when you have 2,000. It starts struggling around 20,000 and at 5 million location updates per minute across 70 countries. It falls apart completely. Here's the specific problem. While that database query is running and at scale, it's not fast. Every single driver is moving. By the time the result comes back, the closest driver in the database is already somewhere else. You've matched a rider to a ghost. You can't solve this by buying faster servers. The data itself is moving. You need a completely different way of thinking about what nearest even means. The solution Uber landed on is called geohashing, and it's elegant. This is the part I find genuinely clever. Geohashing is a way of encoding any location on Earth as a short string of characters, and it's based on a beautifully simple idea. Take the world, divide it in half, left and right. If your location is in the right half, the first character of your geohash is a 1. Now, divide that half in half again, top and bottom, 1 again if you're in the top half. Keep going. After a few iterations, you've narrowed down your location to a specific cell on a grid. The more characters in the geohash string, the smaller and more precise the cell. A geohash of length 7 gives you a cell roughly 150 meters across. That's close enough for matching a rider to a driver. Now here's the insight that makes this useful at scale. Instead of asking which of all these drivers is closest to this point, you flip the question entirely. You ask, which drivers share the same geohash cell as this rider? Because drivers with the same geohash prefix are by definition geographically close. You've converted a distance calculation into a string comparison, and string comparisons are fast. Uber takes this further using Google's S2 library. And I'll be honest, this is where it goes from clever to almost unreasonably effective. S2 divides the Earth into a hierarchy of cells at 30 different levels of precision. Unlike basic geohashing, the cells map cleanly to the sphere of the Earth, no distortion at the poles. But the core principle is the same. Divide the world into a grid. Use cell membership to shrink the problem. What geohash precision level do you think Uber actually uses in production? Drop your guess below. I'll pin the closest answer. Uber separates their system into 2 major services, the supply service and the demand service. The supply service tracks everything about drivers, where every driver is, right now, whether they're available or on a trip, their vehicle type, their rating, their expected location in the next few minutes. This service is being updated constantly. Every driver's app sends a location ping roughly every 4 seconds. The demand service handles everything about riders. Incoming ride requests, matching requests to the right driver pool, managing the state of a trip from request through completion. Both services share a Redis layer for current driver positions. Here's why Redis specifically. It's an in-memory store. The data lives in RAM, not on disk. A Redis lookup for a geohash key returns in under a millisecond. At 5 million updates a minute, that's the only thing fast enough. These 2 services communicate through Kafka, Uber's event streaming backbone. Every significant event fires as a Kafka message. The services that need to react to it pick it up independently. And here's why that isolation matters. If the demand service goes down, say, a bad deploy at 9 p.m. on a Friday, The supply service doesn't care. It keeps ingesting driver locations. Kafka keeps storing the events demand missed. When demand comes back, it drains the queue. Nothing was lost. This is the kind of design decision that looks boring on paper and saves your job in production. So, a ride request comes in. The demand service has the rider's location. It converts that to a geohash, queries Redis for all drivers in that geohash and its neighbors, and gets back a candidate pool. Now it has to pick one. The obvious move is to pick the closest driver by straight-line distance. This is wrong, and it's wrong in a way that seems obvious in hindsight, but apparently took some real-world pain to fully appreciate. The closest driver on a map might be separated from the rider by a motorway or a river. The driver 2 blocks further away might have a clear road. Straight-line distance tells you nothing about how long it actually takes to get somewhere. Uber's ETA engine calculates actual road-based estimated time of arrival for each candidate driver. It uses a road graph, a map of every road, every junction, every traffic signal, and runs a shortest path algorithm to get a real ETA, not a crowfly's estimate. The ETA engine also uses real-time traffic, pulled from the movement patterns of active Uber drivers acting as anonymous sensors on the road network. If drivers are slowing down on a particular road right now, the model knows. You've got a distributed traffic sensor network running for free as a side effect of normal operations. I find that genuinely elegant. Once a driver is selected, the dispatch request goes out. If the driver accepts within a few seconds, the match is confirmed. If not, the system immediately moves to the next best candidate. This process, from request to first dispatch, happens in under 1.8 seconds. Surge pricing is the most complained about feature in ride-sharing. It's also mechanically one of the more interesting parts of Uber's real-time system. Let me show you what's actually happening, and you can decide what you think of it. Every geohash cell has, at any given moment, a supply number and a demand number. Supply: how many available drivers are in and near this cell. Demand: how many ride requests have come from this cell in the last few minutes. When demand exceeds supply beyond a threshold, Uber applies a multiplier to the base fare for trips originating in that cell. The multiplier isn't set by a human. It's calculated automatically based on the ratio. The economic logic is, higher prices attract more drivers to the area and reduce demand from price-sensitive riders until supply and demand rebalance and the multiplier drops back down. It's a feedback loop running automatically across thousands of cells simultaneously. Whether that's a fair way to solve the problem or whether it just means the people who can't afford 2 times get left standing in the rain is a genuinely contested question. Drop your take in the comments. I'm curious what people actually think. A system processing 5 million location updates per minute has basically no tolerance for downtime. A 1-minute outage during peak hours isn't just annoying, it's potentially hundreds of thousands of failed matches. So let's talk about how they build for failure. The dispatch critical services, supply, Redis, the ETA engine, are replicated across multiple AWS regions, not just backed up, actively replicated in real time so a second region can take over immediately if the primary has a problem. For driver location data specifically, the most volatile, most continuously updated data in the system, Uber uses a write-ahead log. Every location update is written to the log before it hits Redis. If the system crashes mid-update, it replays from the log on recovery. 0 position data lost. The guarantee sounds simple. Delivering it at this throughput is not. Uber also runs continuous load and chaos tests in production. Same philosophy Netflix pioneered with Chaos Monkey, which we covered last episode. The idea is simple. If you only find your failure modes when real users experience them, you're already too late. All right, let's run the whole thing. Every hop, in sequence, in real time. Your app sends a request to Uber's API gateway. The demand service receives it. Your pickup location is converted to a geohash, a short string that places you in a specific cell on the grid. Redis is queried which drivers are in this cell and its neighbors. The candidate pool comes back, maybe 20, maybe 80 drivers. The ETA engine calculates road-based arrival times for each one, incorporating live traffic. The best match is selected. A dispatch notification fires to that driver's app via Kafka. The driver sees the request. They accept. The demand service confirms the match. Your app updates. Driver name, photo, plate number, live tracking begins. From your tap to that confirmation, under 2 seconds. And it's not 2 seconds because the hardware is fast. It's 2 seconds because every architectural decision in this system, geohashing, Redis, the supply-demand split, the ETA engine, was designed specifically to make those 2 seconds possible. Uber built this not because it was the obvious solution. They built it because the naive solution, query a database, return the closest row, breaks at the scale of millions of simultaneous location updates. Geohashing, so location becomes a string comparison, not a distance scan. Redis, so driver positions live in memory and return in microseconds. A supply and demand split, so the two sides of the marketplace scale independently. And an ETA engine that treats roads as a graph, not a grid. Each of those decisions exists because something broke first. That's the thing about great system design. It doesn't look clever when you're building it. It looks like fixing a thing that broke, then fixing the next thing that broke, until eventually you have a system that works at scale. Subscribe! Next video is WhatsApp, how they deliver 100 billion messages a day with 2 engineers per server. That ratio is not a typo. I'm going to show you exactly why it was possible and why most companies couldn't replicate it even if they tried. Subscribe so you don't miss it.